Thanks to the organizers of Pi Gotham for putting on this conference and for having me speak. My name is Alec Barrett, and by day I'm a JavaScript developer at 2N, a data visualization firm here in New York City. The project I'm going to talk about is originated about 8 months ago when I was studying at the Recurse Center here in New York. In accordance with RC's mission, I wanted to become a better programmer, and I also wanted to learn Python. Meanwhile, I've been regularly doing the New York Times crossword for a couple of years now. Does anyone else in here do the New York Times or another crossword on a regular basis? Good to see some fellow enthusiasts. And so I wanted to spend some time thinking about how clues and answers in crossword puzzles work. So I set out to build a program in Python that could solve the New York Times crossword. I'll start by talking a little bit about how the crossword works, the task, natural language processing, which is the main method I used, and some particulars about the solver I wrote. So the New York Times crossword, some of you are already familiar, but it's an American-style crossword, which means that each letter is part of a word that goes across and one that goes down. There's a puzzle every day of the week, and they get more difficult as the week goes on. Monday is the easiest, Saturday is the hardest, Sunday is somewhere in between, though it uses a larger grid, 21 by 21 instead of 15 by 15. On a typical 15 by 15 grid, there are between 75 and 85 usually clue answer pairs. This past Monday's puzzle, which is the one I'll be focusing on today, had 76. So what makes a crossword puzzle difficult? The length of the words, the obscurity of the answers, the use of wordplay or words that have multiple meanings. What makes a solver good at crosswords, conversely, is having a large vocabulary, an encyclopedic knowledge of names and terms from a wide range of topics, and the ability to think laterally across multiple associations, as well as the ability to constrain your thoughts based on the length of the words and the letters that are already available in the puzzle. A few more idiosyncrasies about crossword puzzles that are worth mentioning. Clues contain contextual information about the answers. So singular or plural, verb tense, abbreviations in the clue will indicate the same in the answer. Clues can also refer to other clues. So for example, this puzzle had 28 across, slippery, 1 across. So that's impossible to answer confidently unless you know something about 1 across, either its clue or answer. So some of these tasks are better suited to a computer than to a human, like searching through a thesaurus or filtering a long list of words based on conditions like length and matching letters in specific places. Other tasks like interpreting puns or considering pairs of answers together are not impossible, but are going to be harder for the machine. My strategy was to write a program that would generate for each clue in the puzzle a list of candidate answers that fit the size of the corresponding space. I believe that given a list of possible answers for each word that includes the correct answer, the program should be able to identify the correct answer based on the intersecting candidates that contain the same letters. So for example, we would be confident in our answer fish for 1 across if we found intersecting candidates that have F, I, S, and H in the intersecting down spaces. I used 5 different methods to build up the list of candidates: the Google Knowledge Graph Search API, the Wikipedia Search API, a dictionary and a library called PyDictionary, WordNet, which comes from the Natural Language Toolkit, NLTK, and word vectors with a library called Spacey. I think about these methods in 2 different groups, the encyclopedias and the dictionaries. So the first 2 sources will try to find answers that are informationally related to their clues. The Taj Mahal is made of marble. There is a physicist, Enrico, whose name is Fermi. These will often involve proper nouns, either in the clue or the answer or both. The other 3 will try to find answers that are semantically related to their clues. A term for bundles of hay is bales, or an artery is another word for a major highway. These will tend to be words that can be found in a dictionary, though it's in these cases that tenses and pluralization also matter more. I made some determinations about which methods to use on which types of clues. So there are practical limitations. For one thing, I can't search for synonyms if there are multiple meaningful words in a single clue. Some clues also provide a blank space, suggesting that there's either a common phrase or a proper name that the answer will complete. This table shows the different conditions that my program checks when deciding which methods to apply to each clue. In the case of clues that reference another clue, I'm just skipping those for now. In the case of a single word, I'll use the dictionary, the word net, and word vectors. In the case of space in the clue, such as the clue blank of sandwich, I pass that to the knowledge graph, the Wikipedia search, and also word vectors. And otherwise, I will use those three, knowledge graph, Wikipedia, and word vectors. Plus, if I can extract a single word that seems to be the most meaningful word in the clue, then I will also pass that to the dictionary and the word net. A good example of that is the clue distort, comma, as data, where if we drop everything after the comma, the word distort might still be closely tied to the correct answer. So sort of the most interesting things I learned from this had to do with the natural language processing libraries, NLTK and spaCy. I'll talk about these in detail. I also don't want to give anyone false hope, so I'll spoil the surprise. The program does not currently solve a full puzzle. I'll explain later what some of the limitations are. But some of what it is able to do is pretty remarkable, and it gives me hope that these methods, with continued iteration and refinement, could eventually get me there. So natural language processing, or NLP, as I mentioned, I used two libraries. The Natural Language Toolkit provides access to WordNet, which is described as a lexical database of English. I first learned about NLTK from a fellow recursor who was building a project with Markov chains, which, if you think about it, is a different sort of word association task. NLTK has a repository of large English language corpuses for tasks like these. For my purposes, it was useful in that it exposed relationships between words that are more complex than just synonyms or antonyms. WordNet lets my program take a one-word clue and explore a network of words through relationships like hypernyms, things of which this word is an example, root hypernyms, the most general thing of which this is an example, hyponyms, things that are examples of this word, and member holonyms, things of which this word is a part. And as you can imagine, those are sort of going up and down a tree of specificity. So this is the code that I use to sort of perform this search through the space. The sort of key line here is I'm taking a list of the attributes using the get attribute method to see if each synonym has that. So first check if it exists, and then I'm actually getting it. And one thing I realized after playing around with this for a little while is that the answer that I'm looking for may not be in the sort of first hyponym set, but that sometimes I need to iterate a few levels deeper and check the hyponyms of hyponyms and the hypernyms of hypernyms. And so it's got this iteration function where I will let it go up to 3 levels deep before sort of giving up the search. So for example, a clue in this puzzle was somersault, and when you check the WordNet synsets method, it gives you somersault as a noun and somersault as a verb. Okay, fair enough. If we take the verb and look for its hypernyms, we'll see that roll over is a sort of general form of the verb to somersault. The root hypernym, the most general thing that somersaulting is the verb move. Okay, so that's useful. And then if you sort of call that function I just showed and iterate through all of the possibilities, you get this long list of both nouns and verbs. And sure enough, the correct answer, the 4-letter answer that I'm looking for is flip, which actually shows up pretty early on. So this was a successful use of this method. Another application of natural language processing is to parse clues to separate high signal words from filler material. So natural language processing has the concept of stop words, which are common words that can be removed while preserving the original meaning of the phrase or sentence. So this here is the built-in NLTK list of English stop words. As you can see, they're some of the most common words in the English language, including some contractions and articles and prepositions and conjunctions. So both NLTK and spaCy also provide part of speech tagging, which is useful because it lets me weed out words that are unlikely to be directly related to the answer. And also, as I mentioned earlier, because details about the clue are relevant to determining the answer. So a plural clue indicates a plural answer, past tense indicates past tense. So if we take, for example, 41 down from this puzzle, butcher's offerings, pay attention to the S. It's a 5-letter answer. So if we were looking through this space, we would quickly discard the word meat, because that only has 4 letters, unless we were considering that there's going to be an S on the end, or a plural form of the word that we're looking for, and meats is in fact the correct answer. This is also relevant to processing the encyclopedia methods as opposed to the dictionary methods. The search terms that I'm passing to Google Knowledge Graph and Wikipedia include different formulations of the clues. So we can see here, applying the part of speech tagging to butcher's offerings will separate butcher, the noun, the possessive, offerings, the plural noun. One sort of quirk that I noticed is that the capital B makes it a proper noun, whereas a lowercase b makes it a common noun, and that's not a meaningful distinction that the crossword is trying to send us. It just, the New York Times capitalizes the first word of every clue. So that's something we sort of had to work in. And another example, jump in an ice rink. If I apply the part of speech tagging and filter out anything that is not a noun, we end up with jump ice rink, which I think, and the evidence bears out, is more likely to get me the correct answer. On to word vectors. Spacy, the second NLP library I used, describes itself as industrial strength natural language processing. So among its many features are an API for word vectors, which is trained using the word-to-vec algorithm that you may have heard of. This library has a 1,000,000-word dictionary built on a project out of Stanford called GLOVE, which stands for Global Vectors for Word Representation. In order to perform mathematical operations on words, they're represented as vectors in 300-dimensional space. So for practical purposes, that's an array of 300 numbers. None of these values has any inherent meaning, but they can be added and subtracted, which is the key to this process. The most famous illustration of word vectors that I've seen, which at this point is maybe a little bit cliched, is the expression king minus man plus woman equals queen. Has anyone seen this example before? So, so here's an illustration of what the vector for king is, and the other 3 words are similar. But it's worth unpacking this a little bit. If you take the vector for king, subtract the vector for man, add the vector for woman, the result isn't a word, it's another vector. And it is not, in fact, I suspected, the exact vector for the word queen. We can show that it's not by doing the arithmetic and then checking the difference between the true vector for the word queen and the result of the addition and subtraction. We would expect this to be all zeros if they were in fact equal. So what's actually happening is that we're left with a brand new vector that does not represent a word in the vocabulary. It represents a position in 300-dimensional space. The task then becomes how to find the vocabulary words whose vectors we know that are closest to that result position. And to do this, we use something called cosine similarity. This is the formula for it, which I found online, and I'm not an expert in, so I won't try and explain it in detail. But the point is that next time you hear someone say king minus man plus woman equals queen, what they should really be saying is the difference between the expression king minus man plus woman and queen is less than the difference between that expression and any other words vector. But that is a little less succinct. This is the function I wrote to do this vector addition. I don't have anything to subtract, but I take a crossword clue, add the word vectors together, and then look for other words in the vocabulary that are close by. So we're just searching the vocabulary words of a given length, right? Because we know how long the answer is going to be. But that still means we're taking the entire vocabulary list of words of that given length, sorting it in order of closeness as determined by cosine similarity. I only do that once, but it still feels a little inefficient, though it happens to be very fast. So just going line by line, we take the vector of the clue that's passed in. We use a reduce to add up all the vectors together. We filter out the vocabulary because the answer in the crossword is never going to be a word that was in the clue. and I also want to remove contractions, so anything with an apostrophe. And then sort based on the cosine function I showed a moment ago, and then return however n many, which I'm usually using 10 or 20 of the closest words. So I'll work through an example from this Monday's puzzle, plan that is hatched. This was actually the only case in this Monday's puzzle that where word vectors got the correct answer, but none of the other 5 methods I used got the correct answer for that clue. So it is adding some unique value to my program. So if we pass in the clue, plan that's hatched, and then, as I mentioned, go through a couple of different formulations, sometimes only nouns, sometimes nouns, adjectives, adverbs, and then print out the results, we'll see a few of these different possibilities, these candidates. The correct answer that you'll see in several of the cases is the 6-letter word, scheme. And so this was, as I said, a successful application. In some weeks, word vectors do a lot better. A couple of weeks ago, there were several great examples from the September 18th Monday puzzle that I think is particularly well suited to this audience. 41 across, counterpart to if in computer science. It's a 4-letter word. Anyone want to take a guess? Yes, it is else. And the vector method also solved this one. So here are a couple of applications of it. If you take the phrase if computer science, that gets you else as one of the options. Though it also turns out that if you just take the word if, that gets you a vector that is very close to the vector for the word else. So in some cases, all that matters is that the word has one vector that gets you close to the position in space that you want to be, and the rest of the words don't pull you too far away in some other direction. Another thing I noticed in working through this example was if you just pass in counterpart, right, which is part of the original clue, you get this list of nonsense words, including derp and prob and zerg. And again, remember this is filtered for 4-letter words. What it turns out is going on here is that there is no vector for the word counterpart in the library that I'm using. So obviously this only works in cases where the library has the vector. Another quick example from the same puzzle, dairy animal, looking for a 3-letter word here. And it turns out that the sum of the vectors for dairy and animal get us this list, but dairy alone gets us this list, which has a lot of the same answers, and animal alone gets us this list, which has a lot of the same answers. And sure enough, the correct answer is cow, which shows up in all 3 cases. So there is some redundancy in this method, but I'd rather that than the other way around. All right, on to the solver. I built a couple of utility functions to create this data pipeline that gave me access to the clues. The New York Times does not, as far as I know, publish an archive of crossword puzzle clues and answers. So I'm grateful to the blogger behind nytcrossword.com, which I scraped using Beautiful Soup to download both text and images of the crossword puzzles. It's maybe a little bit fragile to rely this much on a third-party resource. The site upgraded at some point over the summer, and I briefly panicked when I realized it wasn't working until I figured out that the format of the URLs had changed, and I just needed to, move some strings around. So the images on the blog are hosted in PNG format, and in order to locate each clue and determine which answers intersect with each other, I needed to parse the image, in particular to find the black squares. So I also had some fun with Tesseract, an optical character recognition library, which allowed me to extract the answers directly from the image of a completed puzzle. I didn't necessarily need to use OCR to do this because I could get them directly from the text of the blog, but I needed to scan the image somehow, slice it into 15 rows, 15 columns, in order to know where the black squares were located. Once you know their locations, it's fairly easy to determine the XY coordinates of each answer. It's a little like the game Battleship. If you know the starting position and the length of the thing you're looking for, then you know where the rest of it is. Here's the function I wrote to perform the OCR. Basically, we're just looping over 15 rows, 15 columns. there was a little bit of a hitch where, as you can see, there are in each square also the numbers of the across or down clue that answer is associated with, and the OCR does not like that, so I needed to crop the cells a little bit narrower. And another hack that I came across was that for some reason the letter I was not getting recognized, so I needed to default the program to I if it wasn't being found, if a letter was not being found. But here's the output of the OCR. It's fairly fast, 36 seconds for a full puzzle, so 2 seconds give or take per line. And it's pretty cool to watch. So it now has all of this information about where the answers fall. So as I mentioned earlier, the program does not currently solve a full puzzle. It generates a set of candidates that contain the correct answer for about 42% of the clues in the case of this past Monday. Some weeks it's a few points higher, some a few points lower. That was 32 out of the 76 answers. So I did some analytics on the methods to see which ones are getting those hits. Turns out Wikipedia is actually the strongest, which makes some sense because it's got factual clues from the encyclopedia function, but it's also going to know some things about language because of expressions and idioms that might be present in the pages that'll come back in search results. With that said, every method is making a unique contribution, and this table gets cut off, but this is the answers that were found and which columns or which method found it. And so, so every method is pulling its weight. I know how well the program is doing because I can search for the correct answer in the candidates, but my program doesn't have access to that information because that would defeat the purpose of creating a solver. It has to use the same method a human would use, which is to look at the intersecting clues and see if it makes sense with the other answers that are available. So it's hard to determine which candidates are the correct answer if we don't necessarily have the correct answer for the intersecting clues, right? And I think about this problem a little bit like the push-up square. Everyone needs to be lifting at the same time in order for the thing to get off the ground. There is some circular dependency where the answer, finding the correct answer depends on being able to find the correct answer for the intersecting clues. And we can only do that if a lot of the correct answers are available in the candidates. There's an academic term for this, which is a constraint problem, and it turns out that there is some literature out there that I won't go into about applying this method to crossword puzzles. So in conclusion, my top priority for this project is to get my hit rate up above 50%. Until I can do that, I don't have much faith in the program's ability to actually solve a full puzzle. I don't think I need 100% of the answers to be somewhere in the candidates because some of the answers should be able to be found just by looking at the intersecting letters the same way a human solver would do it. For example, if we had a 15-letter multi-word answer, which is going to be hard for a computer to come up with, but 10 or 12 of the letters are already found, we might just be able to narrow it down based on the English words that fit into those spaces and ignore the clue altogether. So some ways I might be able to improve the hit rate, just try more formulations. Sometimes these things are finicky, and including a punctuation mark or not might make the difference between whether the method returns the correct answer or not. I haven't yet looked to see if there's sort of a systematic pattern to which types of clues are not getting found, but it's possible that a whole new API or technique might be able to tackle a substantial number of them. Another avenue I hope to pursue is machine learning. With access to years' worth of clue answer combinations as training data, it's possible that the program could make some of those indirect associations between clues and answers. The downside is that then we have the black box of the model and we don't necessarily know how the connections are getting made. It also seems intuitively very hard compared to a task like image classification where you have, 1 or 20 or 100 classes that you're trying to put the images into, versus here where the possible answers are, every English word in the dictionary of a certain length, plus names, phrases, abbreviations. So the outputs are much more varied. But machine learning would definitely be able to help with some of these abstract things like themes, multi-word answers, puns that are hard to write explicit instructions for a computer. And finally, it's possible I'm approaching this the wrong way. I'm trying to write a program to solve a crossword puzzle the way a human would solve it. Look up clues in the brain that you have access to and find the corresponding answers that fit. Maybe I should be considering approaches that are only available to a computer which has access to the entire English language, like examining the large but finite number of states of crossword puzzles that exist and narrowing them down through a process of elimination for things that are not grammatical, nonsense words, or non-existent words. Thanks so much for coming. The code is on GitHub, and that's my tag online. Thanks a lot.